like a little bit about this system. I'll turn the volume down a little bit here. And then we'll get right into it. So we have a model for our motor. Let's call y the angular velocity of the motor. That's our output that we're measuring. And then the input u is a voltage. And then we got a model for this, a discrete time transfer function. And it looks like this. So it's a first order discrete time system, and we're assuming that the sampling frequency is 20 hertz. And that's what we're gonna run on the system today in real time. Okay, so all of you came up with controllers of this form. So D is the controller transfer function. And remember, this transfer function is the ratio of the control output, U, which is a voltage, to the error, E, in the output signal. So E is the difference between what we want the angular velocity to be and what it actually is measured to be. So you guys designed a controller that is a control gain multiplied by a 0 over 2 poles. And so if you want to run your controller today on the Google form, you have to tell me what's your gain and what are your controller parameters. And then I throw it on the Arduino code. So how do we turn this controller into Arduino code? Let's see. Well, I don't want to write out all the steps because it would take me like 2 or 3 minutes to get there. But you guys know how to do this. You take this transfer function. The Google form link doesn't work. It works, because I have people who have filled it out. Sometimes the links on UB Learns aren't, if you click directly from UB Learns, it's not great. But if you open it from like your email, because it'll be in your email, or yeah, Eric says right click, open in a new tab. So there are ways. Okay, anyways, we can turn this into a difference equation. So the controller voltage at step K, so U at step K, it's going to be P1 plus P2, so your 2 poles, times your voltage from the previous time step, minus the product of your 2 poles times your voltage from 2 time steps prior. And then we have another term here. You take your control gain times your error from the prior time step minus your 0 times the error from 2 time steps prior. So, like, looking at that equation, it's like, good grief, that's a little complicated, but that's what it is. That's what we've designed here to satisfy some certain constraints. So let's go to the Arduino code, and I'm going to show you where I put in this control. Let's go. Okay. Let's go over here. Let's see. Can you see this? Maybe if I zoom in like a little bit more. Wait, where am I? Like, okay, preferences. Font size. It's only 19. What if we make it 24? Okay, that's better. So you can see I already pulled some controller parameters from the spreadsheet. Does that make you nervous seeing your name there? Oh my goodness gracious. No, don't be nervous. It's fine. Okay, so let me show you in here where we put in the controller. So right here. This is the difference equation. I'm going to make this even a little bit bigger. There we go. So this is the difference equation we just wrote down, and it's a function of your poles and your zeros and so on. Okay, so we're gonna run a combination of 3 types of tests. We can do a step reference, we can do a ramp reference, and then one of these is a potentiometer where I'm just gonna like randomly control the reference by using this potentiometer. Like I'll just move this around and that'll change the reference speed. Okay, so why don't we just get like right into it? Let's get right into it. You still have time to enter your controllers on the Google form. I'm just gonna like go through in the order that I received these. Ken, this is you. Are you here? So we have, and this is fun to see too, like everybody's parameters are really different, but I think all of these, the majority of them will work. Let's do a step input. So we'll run that. I'm gonna upload this code to the board. I'm gonna plug this in. It might get a little loud. Okay, you can see it's spinning up. Let's go to the serial plotter. Oh dear. Okay. So let me tell you what's on the screen. This is working, by the way. So the blue line here is the reference. I'm doing like an alternating step. The green line is the measured angular velocity. So you can see that Ken's controller, it's overshooting a little bit, and then it approaches the steady state value, and it's doing really great. The red line is how much voltage we're sending. So, congratulations, Ken, this works. How much overshoot did you want in your controller? Does this look like what you expected? All right, let's do, it works, yes. How did I zoom in like that? I just maximized the window for the plot. Okay, I'm gonna move on to another one because we have a couple, and I wanna try to get a lot of these in. So I'm gonna move on to the second controller, but we'll do let's do like a ramp. Derek, you're next. Let's upload your code. Let's go here. Wait, I might have unplugged something. Oh! Ooh! Okay, this one has some extra oscillations in it. Is this how your simulation responded? Let's try a ramp. I mean, it is approaching 0 steady state error. What motor model is that? It's just a first order transfer function. I'm gonna try a ramp here. So I'm gonna change test to number 2. Let's go back. So now we're trying to follow this blue line. Oh, the physical motor. This is just a 6-volt DC motor. And actually, I don't even know where it came from. The marking on the side is a little faded. Okay, we can see that this is tracking a ramp decently, but this controller definitely has some. The spec should give you parameters for the ODE model, not for this motor. I can tell you that much. Okay. Jared. Let's upload this. You're next. Looks like we're gonna do a ramp for you first. Ooh, look at that steady state error on the ramp. It's like right on top of it. Okay. How about we try changing the reference with a potentiometer? So right now, I'm sliding a potentiometer around to randomly change the reference signal. Let's zoom in a little bit more. The camera's a little bit in the way here, but you can see at the far right of the screen, I'm kind of randomly adjusting the reference. I'm keeping it in between the camera windows on the right. So you can see we design a controller maybe with a step reference in mind, but it'll work decently for a range of reference signals. Nice. Okay, Jared, your controller looks great. Let's slow this down. All right, I'm gonna move on. Kyle Kane. Let's go back to a step. Let's run a step reference for you. I love engineering too, Atom Fighter. This is a lot of fun for me. I love control systems. I hope you guys enjoy it too. Wait, what did I do? Oh, now it's working. Ooh, this is working nice. We have a little bit of overshoot for the step response. No real steady state error to speak of, which we know is we put a pole at +1. Looks great. Yash. Are you here, Yash? We're gonna do you next. Let's see. It's just taking a second. Oh, Kevin Ventura. Welcome, my friend. Long time no see. Ooh, this controller is smooth. Look at this. Very little overshoot. It just goes right to the reference speed. Yash, I like this controller. I mean, if you guys had this motor yourselves when you're doing this homework, you would probably tweak it, dial it in where you want. So this is kind of just, imagine this is your first iteration. All of you in real life would have the opportunity to go back, tweak things a little bit. But I really like this one. This looks great. Okay. Tim Nichols. And after Tim is Cody, then Mohammed. Are you here, Tim? Your gain is like 5. That makes me, I don't know. Whoa. That seems a little dubious to me. This red line is the voltage that the controller wants to send to the motor. It wants to send like a kilovolt, which there's stoppers in. I mean, I don't have a kilovolt here, so it's not going to do it. There might be a typo in in your parameters. A gain of 5 is pretty steep. Okay, this is to be expected. This will happen with some controllers. This is great for a drag race burnout. Okay. Let's all right, Cody, let's try yours out. Holy smokes. That controller is ready to burn. Ready to burn some tires. All right. This one, I think it'll be a little more subdued. Okay. Very clean. This is great, you guys. All right, let's try a ramp with this one. We're just playing around here. We're just having a good time. I wonder what the average of all those parameters looks like. Oh, yeah. No, that's... We could try that. It'll probably be a scary cocktail. Okay, you can see where we're tracking a ramp here. And Cody, this looks nice. Are you in the chat with us today? Are you satisfied with your performance here? So you can see some steady state error when we're tracking a ramp. That is expected for a controller of this form because we only have one pole at z equals 1. So we'll never be able to track this perfectly. But I mean, in practice, this is pretty darn close. Okay, nice job, Cody. Looks great. Nice job to all of you. This is a fun experience. Okay, so we're going to Mohammed Abedin. We're going to start with a ramp because that's just where we were. So this one has a little bit more steady state error for the ramp. You can already see that. So it's a little less aggressive. All right, let's try a step with this one. I'm curious. So we'll go back to test style number 1. We're going to look at the step response. Okay, okay. So this one has a little bit of a longer settling time. To be expected, looking at the ramp, it was a little bit lagging behind. So this one still gets to the target speed. It just settles a little slower. Okay, Toan. Let's try yours. I know you wanted to try yours out. I had you in mind when I was thinking about what are we going to do today. Toan was interested in seeing these controllers. Ooh, this looks great. This has like very little overshoot. A snappy settling time. It's interesting how it has this little like contour right here. Oh, I guess that's not really happening every time. But this is smooth. No steady state error. Goes straight to the... Let's try... Let's put it through the paces. Like, I'm just going to give it like a random reference to follow. Using this slide potentiometer over here. Does less overshoot typically lead to a longer rise time? Yes. I would say yes. In biomedical engineering, we study similar responses to systems. For example, in emergencies, we desire systems with small 5 tau settling time, great. While for monitoring, it's okay to be big. Oh, that's very cool. Thanks for sharing that. It's always cool to see the connections. I mean, controls engineering, obviously it's relevant to so many disciplines of engineering. I mean, we're doing it for a mechanical system, but Tia, are you here? Tia, we're going to do yours next. We're going to start with like a random reference that I'm going to give your controller. All right, so let's go here. Let's pull up the plotter. Whoa. This this follows the reference that I'm giving really tight. This is great. It's like really snappy here. You can see there's like This probably has a really great KV. I bet it tracks a ramp really well. Let's try a ramp. Great controller, Tia. This is really good. This is really great. Let's pull this over here. Okay, so it has some overshoot at the beginning. So that's a general trend, I think. Like there's a trade-off. Hell yeah, I was super nervous. No, this is great. I think, yeah, this controller has great steady state performance. As you can see, like it's kind of right on top. I think if we do a step, it's going to have a lot of overshoot, but that's okay. This is our first iteration. Just imagine you would go back and change this to dial it in. Okay, so when we do a step, this controller has a little bit of oscillations at the beginning. But it's okay. Very nicely done. All right, Eric Moran. We're gonna try yours. We're gonna do a step first. Let's go here. And then after this is gonna be Dylan Bellamy. And then we're gonna have we're doing a ramp, I guess. Or wait. Ooh, this one? This one's just a little slow. Like if we look at this one, the poles are around 0.9. Or wait, does that? No, these are open loop. But I just think this controller, it's approaching the steady state value. It's just doing it a little slowly. So for this one, we would want to speed up the settling time a little bit. That is quite all right. All right, Dylan, let's try this one. Let's see. Okay, there we go. Ooh, this one has basically no overshoot to speak of. This is another smooth controller. This looks good. How does it do on a ramp? Let's check. And then we'll move on to Annie's controller. Are you here, Annie? Whoa, Dylan, very nice. Very nice. Tracking that ramp looks great. Looks fantastic. Let's try Annie's. We'll start with the ramp response here. Okay, so we're gonna have some transient stuff at the beginning, a couple oscillations, but this is really tight in the ramp response. So as far as like steady state performance is concerned, this is very great in the steady state. If we do a step, it'll have some overshoot. That's okay. It'll shoot up in a second, I think. There we go. So just a little bit of overshoot at the beginning, a little bit of transient here. All right. Jeffrey Chin. Let's try yours out. Ooh. It's okay. This one we have some sustained oscillations here. Let's try a ramp though. Oops. totally normal for a first iteration of a controller to have some stability issues. Okay, that's what we got going on here. This one's going a little crazy. That's okay. We'd go back and tweak that a little bit. Totally normal. All right, Dakota. Let's try this out. And then I'll pull a couple more controllers down. Like I know some of you probably just put them up in the last couple minutes. Ooh, this is tracking this ramp very nicely. Very tight. Let's try it. Let's try a step. We're gonna do a stepper. Okay. We get one overshoot. Looks like, I don't know, what is that, 25% on the hardware? And then it settles right back in. Okay, we'll do a keel, and then I'll see if we have any additional controllers up there. This is really cool, everybody. I hope you enjoy seeing some of the fruits of your labor. I mean, we designed these on paper, but it's cool to see, like, no, this is this works on real hardware. It basically, the controller comes down to putting that one line of code in here. This one is, I like this controller. A keel. Look at that. It's pretty snappy. There's no overshoot. Keel says, "Oh baby, it works good." Yeah, it does. I want to try using the potentiometer to give it some like random reference. We'll run it around a little bit. Yeah, you know, it's interesting the trade-offs with these. Like, there's a little bit of lag with this one when I like create a sort of ramp signal. Like you can see that there's a little bit of lag between them. But when it comes to like a step, it looks really smooth with that. How do we make adjustments with rise time? So the rise time, well, the rise time, remember, that's going to depend on where you place your closed loop poles. Like, we have that code that shows you the acceptable region for certain rise times. I think generally you have to increase the natural frequency of your closed loop poles. So that means like kind of even pushing them into the right half plane of the Z-plane, something like that. Okay, I'm gonna go over here. I'm gonna go over to our spreadsheet. Oh, we added quite a few here. All right, we'll put that in there. I'm just pulling some of these down. Okay. Got this. Now I have to copy and paste it into. Okay. Let's go back over here. Okay, so you see we added quite a bit more. Let's see, I'll change this. I think these ones you have to change to a 1.0. Actually, no, that's probably fine. Oh my goodness, Henry Leach, you put a double period in here? How dare you? How dare you? Okay. Oh, I already have a keel. We already did a keel. All right, let's run Nick's controller. My gain is supposed to be 0.0747. You submitted the wrong parameter. Tim, you gave me a 5.1. Were you trying to set my office on fire? All right. We'll run yours again. Wait. Actually, okay, so I have to remember we're coming back to Nick after that. Yeah, remember there's no pressure on this. We're just testing out the first iteration of these controllers. And in my experience, it's normal for there to be some problems. So that's okay. I'm surprised that most of these are working right out of the gate. Ooh, okay. So now, Tim, this is your updated controller. So you can see that's tracking this speed pretty well. Nice. I like it. All right. So let's keep going here. Let's test some more. Nick, that's right. We're gonna test yours. Let's go back to a step test. Okay, there we go. I was like, I don't think this is going. Okay, very nice. No overshoot. Pretty tight settling time. There's a good speed controller right there. Let's go with anonymous. The anonymous controller. He who shall not be named. Lord Voldemort. Ooh, this is very nice. Let's try a ramp with this one. Let's throw a ramp at the anonymous controller and see how it tracks. Pretty tight. Yay. Yeah. Very cool. Very nice. You guys can say you've designed a controller on a real piece of hardware. Ooh, I see a gain of 6. That doesn't necessarily mean trouble, but I think it's going to be a more aggressive controller. This is Andrew. Here we go, Andrew. Let's test it out. Ooh. Oh, I think this one's unstable. It wants us to put megavolts into the system. There might be a typo in that one. Okay, Anthony Marin. that one's for a rocket ship. Okay, no, that is totally okay, Andrew. That one's the Bitcoin stock exchange model. Yes. Hey, that kind of exponential positive instability is desired for certain applications. This looks nice. This is Anthony's. Let's try a step with your controller. Let's see how that step does. When it decides to go, of course. Okay. Looks good. Looks nice. Well done, everybody. All right. There's a controller with K equals 12,312. Don't say that. Henry? Henry! Oh, you better adjust that before I get there. I'm gonna be upset. Might be missing a decimal place. Good luck. Henry Scooch. This is smooth. Put a decimal point in front. Whoops. Now you guys can understand why you hear about stories of some engineering catastrophe. Somebody missed a decimal point. It's just me at the control station. I'm just putting in what you told me. You want to see how fast I can go? Okay, nice. Okay, John Karst. Let's run this. So this should be a step, I believe. Let's get this here. Okay, little overshoot. So that gives us a fast rise time. You know, I guess... No, but overshoot, even though we see overshoot, it's not always tied to rise time. But yes, nice. This is good. Well done, John. I bet this one will have nice ramp following as well. Let's try it. Let's give it a ramp. Look at that buttery smooth response. Tracking a ramp very nicely. Okay. Let's try another one. Ryan, Ireland. We're gonna do a ramp. If you're just joining us, we're just testing out some speed controllers for these DC motors that we built. Because part of the controller design process is, hey, I designed this thing on paper. How does it perform on real hardware? And usually you run a hardware test and you're like, wow, we need to refine our parameters a little bit. Okay, let's try a step with this. But a lot of these are performing pretty well out of the gate. I think that's because we have a decent model for this motor. I mean, it's a relatively simple system. It's first order dynamics mostly. Nice. There we go. All right, let's Joshua, let's try your controller. Joshua Wilcox, let's do it. We'll do a step response first. Nice. Very smooth. Smooth, quick response. That's a great step response. So, Henry, we're gonna do this. You said a decimal point out in front, right? There we go. We have averted disaster caused by the 12,000 gain. We're not gonna have a rocket ship right here. Hopefully not. Very nice. No board smoke. We're not setting the electronics on fire today. Look at this. This is very snappy. Quick settling time. Let's do, let's give it like a sort of random, exquisite, majestic even. Look at that. Following the reference, very nice. Well done, everybody. This is fun. All right, Jacob, let's try out yours. Oops. Let's upload this one. Nice. This one just skates into the steady state value real smooth. So Rob, you just added your parameters? I guess the lag is kind of common for low overshoot models. I think so. I think that's what we're seeing. Like systems with it seems like the systems we've designed with a fast transient, some overshoot, they have nice steady state performance. All right, Christopher, let's try yours out. Oh, this is very nice. Look at it following this reference that I'm giving it. Nicely done, Christopher. No steady state error to speak of. Snappy response. Well done. Okay. Steven, let's do it. Let's run it. Tim Dubill, hope all is well. I miss these demos. Are you still playing guitar? I haven't played as much guitar this semester. You're reminding me to break it out again. Steven, nice controller. This just skates into the steady state value here. Nicely done, everybody. Christopher, you wanted to see the ramp. Let's try it. I can do a ramp for you. And then we'll move on to Carl after that. All right, we're doing a ramp for Christopher. It's doing nice. It's doing nice. Nice controller here. I like it. I know we give root locus a hard time because it's kind of it can be a painstaking design process, but the results, they're here. Okay, so this one's following a ramp nicely. We have a little bit of steady state error in the ramp tracking. That's to be expected. Let's do a step. I bet this will have a real smooth step response based on its ramp. Here we go. Nice. How would we know the constraints for things like overshoot and settling time? Just by looking at a system? You mean like before you design the controller, deciding how much settling time you want? That's up to you as the control system designer, or your client. Like, what do they need out of the system response? This is Alex Hutter. Your controller's coming up. Nice. We got a little overshoot here. You know what I'm curious about? How your control design parameters are linked to the designer's personality. Some of these are like they're quick. They have some overshoot. Some of them have no overshoot. They kind of like skate in to the steady state. I bet that'd be an interesting study. How control systems designers approaching the same problem, how they pick their closed loop poles. Oh, this is very nice. Steady state performance when tracking a ramp. That means it has a large KV. All right, Krishnam. Let's try yours out. We'll start with the ramp. Okay, there we go. We can see this one has a little more steady state error in the ramp than the previous. But that also probably means that it's going to have our smooth step response, little overshoot. There we go. Yeah, I think when you design a controller, given the constraints, there's many possible controllers that can meet the constraints as you're seeing here. Aditya Atre. Wait, did we already do yours? All right, let's try it. Aditya. And then we're going to have Randy followed by Carlos. And I'll do one more check of the spreadsheet to see if there were any last minute submissions. Aditya, very nice. A little bit of overshoot. Let's try some random reference tracking using this slide potentiometer over here. Sure, I'll test your controller. Oh, this is nice. Look at this. It keeps up very nicely with changes in reference that I provide. The red line, once again, that's the voltage that your controller is sending to the motor. That's what's cool about these controllers. It's like it decides the voltage. You just came up with the rules that it follows, and it creates all that behavior. Okay. Randy, let's try your controller. Then we'll do Carlos. I'm kind of giving it a step input right now. Oh, nice. Let's do like a kind of ramp. Nice. Very smooth. All right, let's try yours, Carlos. Let's try it out. Ooh, this one has a little bit of overshoot. The blue line is the reference that it's trying to track. That's the target speed. You can see that we follow it pretty nicely. We got a little bit of overshoot. Well done, Carlos. Okay, let's do one more visit to the spreadsheet. That's what I'm doing in the background here. Okay, I see we have Virgil, Sarab, and we have attempt number 2 from somebody. Oh, whoops. Okay, I just gotta throw this over here. I gotta do this. I gotta copy and paste it into the code. And, okay. Let's go back over here. Let's go back over here. Oh, wait, you gave me some parameters in the chat. Let's try this. Ooh. You're making me do all this. You're making it hard. You're making it hard, not using the spreadsheet. All right, let's try this. Okay, we're almost there. This one is from... That was my best approximation of your name. Your Twitch name. Here, okay. Here we go. Virgil. Let's try it out. This is a good time. Thank you for joining today, letting me test out your controllers. Virgil, this looks great. This is the payoff of the work you do in making a controller. Doing speed control on a motor can be applied to like tons of different problems. All right, let's do Sarab. Look at that, effortlessly tracking the reference that I give it. Very snappy, quick response, a little bit of overshoot, not too much. And if I have a moving ramp, the steady state error is pretty tight. Nicely done, Sarab. Great controller. Okay, this is attempt number 2. Let's try it out. Okay, we still have, I don't know if your first attempt had some of this overshoot. It looks like, you know, when it's the steady state error, if I keep the ramp going, like it's not oscillating during the ramp itself, like it's really tightly following it. It's when I settle to a steady state value that it, oh, that's gonna go unstable. So this means the closed loop poles, at least one of them has a magnitude greater than 1. So if you check your closed loop poles in MATLAB, I think you'll see that their magnitude is outside of the unit circle. Okay, we'll try to quiet that one down. All right, let's do this one. All right, last call for any controllers. I'm getting to the end of the list. So this one is for Chi. That's my approximation at the name. This is smooth. The step response doesn't have really any overshoot to speak of. There's that steady state error in the transitions here, like for a ramp. You can see that difference, that little bit of lag, but it very tightly gets to that steady state value. Well done, everybody. Bravo! I'm happy with these controllers that you made. I'll do one last check on the Google spreadsheet. Just see if any last minute additions. Doesn't look like it right now. I think that brings us to the end here. Well done, you guys. I don't know if you have any questions, comments. Thanks for this amazing experience testing the model. Hey, it's my pleasure to do it. Thank you guys for all the hard work you put into that. I know for many of you, homework 6 was many hours of effort. I know that was not easy. That's not an easy thing to do. So, yeah, I want to give you some payoff. It's good to see your controllers in action. So bravo, well done. This is the type of thing keep in the back of your mind when you're like interviewing. If you interview for some kind of controls position, you can talk about designed a speed controller for this kind of motor. You tested it out on the hardware. Hey, you're welcome. You're welcome. Glad you guys enjoy it. It's a lot of fun for me too. It's great to see all the great work you guys do. Very nice. You were definitely nervous to see it. Yeah. That's all right. Even if yours didn't work out today, like I've been saying a lot, that's normal. Most of the controllers I tried, they don't work out of the gate. You're like, oh, I need to go back, tweak this a little bit. The results definitely did not match what I had simulated. Well, yeah, what were the differences between what you had simulated and what you were seeing on the hardware? I mean, our model is not perfect, but that's our starting point for controller design. So I think seeing some differences, that's normal. Significantly more oscillations were present. My simulation showed overshoot, but only had one oscillation. Yeah. I've noticed that, like, when you go to implement your controller on hardware, it seems like there's certain closed loop pole locations that are more forgiving than others. Like if you do something pretty aggressive, I've found that the results are a little less predictable than what you expected, which I think makes sense. Like if you're doing something that requires the hardware to be really snappy, I mean, we're just using an Arduino. There might be some delay that throws the closed loop poles off a little bit. We're using a little cheaper setup, but yeah, totally normal to see a bit of difference and then just compensate for it. Because some of those differences, they don't show up in your simulation. You can't know until you actually run it on the hardware. Like, we know for this DC motor that it has some asymmetries in it. Like if you spin it one direction, basically it spins differently in this direction versus that direction. Like the same voltage will result in different speeds depending on the direction. So it's hard to capture stuff like that in just a linear model. So okay. Once again, well done. That was a lot of fun for me. I hope you enjoyed it. Cool to see. And we'll get back into state space control on Wednesday. So we'll keep marching ahead here. All right. We'll call it there. Peace. Have a good rest of your Monday. See you in class. Bye-bye.